I'll kick off in about 2 minutes, just wait for any stragglers. Are there any of you who have not filled out the survey about teaching quality, so the Blue Castle survey? If any of you haven't filled out the survey, so bluecastle.nottingham.ac.uk, to evaluate my teaching, I'd be really appreciative of you doing that at some point. The university pays quite a lot of attention to the scores, so we actually get in trouble if we score badly. So if you fill that in, I'd be very, very grateful. Thank you very much. And I also read the feedback very, very carefully. So the numerical scores are one thing, but the comments I actually read very carefully. So if there's anything in there, anything you don't understand or anything like that, I'll very happily change the slides next time around. Right, should we kick off? I think we're all here, aren't we? Yeah, then we can go to lunch like 2 minutes earlier. Right, so this lecture is called Analog to Digital and Digital to Analog Conversion. Now, this is quite an important topic because all devices you interact with in the modern world are basically digital devices. So, all these computers these people are using to look at Facebook are digital devices, but the real world is analog. So this is sort of teaching you to bridge the analog-digital divide. Now then, before we get started, I've been asked to put up a little advertisement. So then, recap of digital signals. So before we get into this topic, what I would like to do is talk to you about digital signals very briefly, just to refresh your minds. So in lectures 1 through, I basically taught you about digital analog signals. And I spent a lot of time talking about these digital signals. They're either 1 or 0. And that's what the signals look like in all computer systems you're going to deal with in the modern world. They're either 1 or 0. Okay, this is what we use to do computation. But unfortunately, the real world, like the guitar here, doesn't work in 1s and 0s, okay? So the real world has these analog signals. So, gentlemen, if you could not talk, that'd be brilliant, thanks. It just makes my job harder. So the real world is an analog world. So the volume of my voice is an analog signal. It can be any value between 0 and a very, very high value. Or the value of the lighting in this room is between 0 and very, very bright. So it's not 1 or 0. Everything in the real world is an analog signal. So what we do is we have to try and, when we capture these signals, here's a sort of an analog compression wave of sound coming from a guitar. It goes into a microphone, and it generates a voltage, and we can see this voltage on some type of oscilloscope or something. But what we need to do is turn this analog signal into a digital signal before we can actually use it in a digital system. So somehow we need to go from this signal to this signal, and that's what this lecture is about, is bridging the analog to digital divide. So this is going from real-world problems to the problems that your computer likes dealing with. So we looked at this example, and I said, all modern devices, no matter how clever they are and how much the marketing says they've got digital written on the front of them, they've always got this analog electronic front end. And we looked at sort of analog amplifiers. We looked at op-amps. We've now looked at transistors. You remember that the man with his wheel. So we amplify analog signals using op-amps, transistors. So we know a bit about this sort of amplifier, pre-amplifier circuit. We also know quite a lot about digital signals because I've taught you digital design. You can design circuits with AND gates, OR gates, NOT gates. You can actually design your own computational circuits if you wanted to. And if you really put your mind to it, you could actually start designing computer chips. It'd be difficult, but you could actually have a go. But what we don't know, so we've done that, but we don't know about this bit between, so this conversion. And that's what this lecture is about, is bridging these two bits of knowledge that you have in your head already. So let's get on with it. Boom. So here we go. From there to there. That's what this lecture is about. So every device that interacts with the real world will have one of these in it. So we've got a voltmeter here. This will have some type of device that goes from an analog signal that you're measuring to a digital signal. MP3 player, again, some type of encoding device to go from analog to digital. Mobile phones, the same. Even the thermometer's got a very cheap analog to digital converter in it. In fact, that's all it is, really. So these are very, very prevalent device, and they're in basically any piece of electronics you might buy or design. Right, converting between analog and digital signals. So I think we've covered that. So before we look at very, very complex systems, like, for example, converting digital music to analog output on a speaker. So before we start looking at music and things like that, let's look at some very, very simple... somebody rattling biscuits there. Yeah, can I have one? No? It's all right. Before we look at sort of converting things like music and speech and stuff like that, what I'm going to sort of start off doing is teaching you to walk before you can run. I'm going to teach you how to just convert single values of binary to an analog value. So we're just going to convert, I'm going to give you one binary number, and we're going to convert this to one analog number. Or we're going to go the other way around, and we're going to convert one analog number to a binary number. And once we can do that, it's not any different to look at music or speech or, you know, sounds from an earthquake or anything like that. So as soon as we can sort of bridge this divide for one number, we're sorted. So let's start off having a go at that. Now then, this is called an R2r ladder. And you might think it's just a bunch of resistors, and it looks really boring, and I'm not interested. However, this is the circuit that every electronic device uses to go from digital to analog. So this is the number one digital to analog converter that the world uses. Okay, no matter what device it is, your watch, anything, it will have these in it. Okay? And what we're going to do, this is an incredibly elegant circuit, and we're going to do the analysis of this circuit, and you'll see why it's incredibly elegant and how it converts from digital to analog. And the only thing it's got in it are resistors. So it's got a resistor here called R and a resistor here called 2R. So we're going to see how this works. This is really, really very nice piece of engineering. Very, very cheap too, because resistors cost nothing, so you get a very, very cheap digital to analog converter. So this is the output. So here's the output, V out. So this is the analog voltage you want to spit out. So this will go from digital to analog, okay? So from binary to analog. These are the inputs. So you put your digital number in here. So you put a 1 or a 0, 1 or a 0, 1 or a 0, 1 or a 0, 1 or a 0. And if by magic, your analog signal comes out there. And we're going to analyze this now. So what we do, so what you could do, or what you normally do is you'd stick the output pins of a chip on here. So you might have maybe 8 legs of a chip going in here, spewing in digital numbers, or it might come from a microprocessor or something like that. But for this example, what I'm going to do is I've drawn just basically a series of switches. So here's a switch, here's a switch, here's a switch, here's a switch. And this switch can either be connected to 1 volt here, so I've got a little battery. So this is all 1 volt, 1 volt, 1 volt, 1 volt, 1 volt. Or this switch can be connected to the earth. So here's the earth. So this is 0, 0, 0, 0, 0. So these switches can decide between 0 volts and 1 volt, 0 volt, 1 volt, 0 volt, 1 volt, 0 volt, 1 volt. All right? So we can generate a binary number with these switches by just turning them on or off. And out here, as if by magic, we should get our analog number popping out. So what I'm going to do is I'm going to analyze applying a digital signal to 2 pins of this. So we're going to analyze this pin, because it's the easiest pin to analyze, and this pin, because it's the second easiest pin to analyze. And then I'm going to say life's short, so we're not going to do the analysis for all these pins. You're just going to believe me. And yeah, I probably wouldn't ask you to analyze the last pin of this in an exam, because it'd probably be quite mean. Although I make no promises. I can't remember what's an exam, so I better not say. So let's apply 1 volt to this pin here. So we've got a number of 1, 0, 0, 0, 0. So this is connected to 1 volt, this is connected to 0 volts, this is connected to 0 volts, this is connected to 0 volts, this is connected to 0 volts. And the game is to try and figure out what is V out for this circuit. What is the output there? Now, it's incredibly elegant, and you'll see how this works. So the first one I'm going to do for you, and then the second one I'd like you to a bit of audience participation. So what we've got here is a potential divider. And we know how to deal with the resistance in a potential divider, okay? So we've got 2R. So I'll put all this is going on the internet as soon as I get back to my office. There's no need to scribble everything down. I don't delete stuff from slides. So we've got 2R here and 2R here. So we know the formula for resistances in parallel, because we learned it at school, is, so the resistance in parallel is 1 over R equals 1 over 1R plus 1 over the other R. So in this case, it's R new is the resistance we're trying to calculate, equals 1 over R2 and over 1 over R2, okay? So we're just calculating the resistance of these two resistors. And the answer we get is R, because a half R plus a half R is R, okay? So we can rewrite these resistors as just one resistor here, okay? So what can we do to simplify this resistor and this resistor in series? Add them together, right? Yeah, exactly. So we've got R and R is equal to 2R, okay? And you'll see how this gets elegant in a minute. 2R, boom. Do we recognize this? What do we do here? We apply that rule we learned at school with 1 over R equals 1 over 1R plus 1 over the other R's, because they're two resistors in parallel. So we analyze this. So again, we go 1 over R new equals 1 over 2R plus 1 over 2R, and R new equals R. So we can simplify all of this down to R, okay? You see why we're only doing it for 2 pins, because it gets a bit repetitive after a while. So now we've got R and R in series. R plus R is 2R. Boom. And then again, we have the same situation, 2R and 2R in parallel. So again, we can use this rule of resistance in parallel to get R. And we get R there. Okay, it's getting a bit simpler. This is getting to be something we can start to analyze and to think what the voltage at V out would be. So we're going to do this trick one more time. R plus R is 2R. Now then, this looks a bit scary, but we can sort of simplify it and make our lives a bit easier. So let's try and just redraw the circuit and make it less scary. I always do this. Whenever I get a circuit that's a bit weird, I just redraw it to something I find I can analyze more easily, or I'm used to. So I'm not quite sure what the next step is, but what I'd probably do is just get rid of these earths because they look a bit weird and connect them together. And I'd probably move this V out into the middle just to make it look a bit easier. So in fact, I'll just move V out into the middle because I think it makes it look a bit easier. And then let's get rid of the grounds because grounds are always connected together. So let's get rid of them. Boom. So now this is starting to look like a circuit that we can analyze and figure out what V out is. So let's just redraw it again to make life simpler again, just to make sure we sort of know what's going on. So I've just redrawn it, just stretched it out a bit. So what's this remind you of? Begins with a P, second word D. Potential divider I heard at the back. So this is just a potential divider. So what will V out be? Can we do that in their head? What will V out be? 2 resistors, same value of a battery. What's the value in the middle going to be? Anybody? Maybe you in the jumper who's talking. Oh, you were talking. It was your fault. What's the value in the middle? Don't know. Oh, come on. Well, it's a potential divider, right? So you've got 1 volt. It's going to be split over both these resistors equally, yeah? So you're going to have half a volt over one resistor, half a volt over the other resistor. So you can just go 2R, so that's the voltage over one resistor, over 2R plus 2R times 1 volt is 0.5 volts, right? So we now know V out is 0.5 volts. So we've turned this incredibly complicated circuit into a simple potential divider circuit just by applying rules for resistors in parallel and rules for resistors in series. Okay? So, that's quite good. We analysed that. It wasn't that difficult. So I'd like you to remember for the next 15 minutes that when you put a 1 here, a 0, a 0, a 0, a 0, you get 0.5 here. And then it'll all become very clear after we've done the next pin what happens. Okay? So this is where I'd like some more audience participation because I've gone through one with you already. So we're now changing the voltage. So instead of this pin being on, we're now making this pin on. Okay? So we've moved the 1 from here to here. Okay? And we're going to do the analysis again. This time it gets a bit harder because our power source is in the middle of the circuit. But it's not so difficult, and we'll work our way through it together. Okay? So let's get rid of those switches because they're complicated. Let's put a 1 volt source here because it just makes Get rid of the switch makes it easy. So where might we kick off with this? What do you think? Where did we kick off last time? Well, I think I'll kick off at this end, because that looks nice and easy. So look at that. And we can go R2 and 2R and 2R in parallel. R is R. Simplify that. So now I want to participate. So what's this together? 2R, yeah, very good. So what we do next? Yeah, exactly. Those two go into R. Parallel goes into R. What's this together? 2R. Now we can't just blindly follow, because now we've got this voltage source like between this 2R and here. So we've got to sort of do some thinking now. So we can't sort of use these rules anymore. So what we're going to do now is we're going to start redrawing the circuit, and we're going to start sort of applying our minds a little bit and trying to analyze the voltage and what voltage we're going to get on V out. Okay? So, yes, get rid of the grounds. I always find grounds massively confusing. So just because everything is earthed together, right? My feet are at the same potential as that dustbin. There's no like, everything in ground is equal. That's the point of ground. So these grounds are always like joined together. So let's join them together. Okay, it gets a bit simpler to analyze. We can start thinking of strategies to deal with this. Some of you might have done this type of thing at school. So what we're going to do. For the moment, let's get rid of V out. So I'm just going to simplify it by getting rid of V out. Okay? So how can we simplify this now? Well, there's a question. If anybody's got a burning, I can hear talking. If there's a burning question, just shout, because I realise that this is quite in depth. Very happy to stop, repeat. Really, really happy to do that. Okay, so let's get rid of this V out. We've now just got a simple resistor network. And what we can do is we can join this R to this 2R, making 3R, okay? It gets simpler. The whole point is simplify everything, because we don't like difficult situations. So again, let's simplify it. So what I've done is I've redrawn this. So I've just basically morphed the wires around. So can you see, we've got 1 volt here, and it goes to 2R, and then the current goes either through here or through here. So these resistors here are actually in parallel. Now, it's just a bit awkward to analyze like that, and I don't like thinking of it like that. So what I can do is sort of flip these resistors up, and we can draw the circuit as like a linear circuit. So you work through this on your own, you'll see what I'm doing. So I've basically moved this one and this one up to the top. And this is starting to become a much more simple circuit to analyze. So let's simplify this. So we've got these 2 resistors here in parallel that, all a bit of a pain. So use this resistors in parallel rule to deal with it. And we get 1.2R, 1.2R. Now we've got a really simple potential divider. Okay, so we can very easily calculate the voltage over this resistor or over this resistor. So let's go. It's getting a bit. I know it's getting a bit intense, but we're going to stop this in like 3 slides, and you'll see where all this fits in. Why we're doing it. So now we can very easily calculate the voltage over this resistor, and we figure out using this potential divider rule that it's 0.375 volts. So that's potential drop over here. So now let's take that and relate it back to our little bit more complicated circuit that we had like 2 or 3 steps ago. So here I've drawn it out in full. So this 1.2R basically represents this resistance and this resistance. So we know there's 0.375 volts over this and over this, okay? Now, this is the voltage we want to find. Now, what does this remind you of? Two resistors in series. It begins with a P, ends in a D. Potential divider, right? So it's another potential divider. So all we need to do, we're almost there, we're almost at the answer. So all we need to do is say, oh, it's a potential divider, and we can calculate the voltage drop over 2R, which is 2R over R plus 2R equals 0.25 volts. Okay? What value did we have before? Can you remember? 0.5, right? That's half of it. Okay? If you think about digital counting, every time you go up 1, it's like, so you go like 1, 2, 4, 8. You always double or divide by 2. So this looks suspiciously useful, and we'll understand why in a minute. So I'm going to tell you now the general result. So this is, when we put this on, we get 0.25 volts out of there. Okay, now then. Now, life's short, so I'm just going to tell you what happens. So first one on, we get so this first switch is on, we get 0.5 volts. Second switch is on, this one's off, 0.25 volts. Turn this off, turn this on, 0.15 volts there, 0.125 volts there. Turn this off, turn this on, 0.0625, turn this off, turn this on, 0.03125. So you can see every time we go in this direction, we're halving the amount of voltage we apply to the output. So it's just a bit like a binary number in that, you know, this is sort of the most significant bit. This gives most voltage, and this is the least significant bit and gives the least voltage. And each value or each voltage that you can put on the output pin with each switch halves in value each time you go from here to here to here to here. So this is looking like an incredibly useful circuit if we want to go from the binary world to the analog world, and in fact it is. So we can also turn the switches on in different combinations. So for example, if we turn all the switches on, we get the addition of all the voltages. So we get 0.5 from here, 0.25 from here, 0.0125 from here, 0.0625 from here, and et cetera, et cetera. And they all add up, and we get 1 volt at the output. So we've made a circuit like this, whereby turning the switches on and off, we can basically select any output voltage between 0 and 1 volt. Okay? So we can very, very carefully grade the output. So here we are, we can turn on combinations. We've got 0.5 and 0.25, and we get 0.75 out. So, you know, you're free to turn on and off any switch you want, and you get the desired output at the out. I think I've told you that, so I'm not going to labour the point. It's sort of binary counting, okay? Now then, so here's our computer or our digital circuit or the output from the digital stage of your MP3 player. And what it has is pins, and it has, you know, a bank of pins with 1 or 0 on them. And you know, if you've got a very expensive MP3 player, you know, it's probably going to have 32 of these pins. So to this, there'll be attached a series of these resistors in this thing called an R2r ladder. So it's R2r ladder, and it looks a bit like a ladder. And because of this resistor network that we've analysed, your MP3 player will be able to choose any voltage on the output between 0 and 1 volts. And obviously, if you wanted to go higher than 1 volt, because 1 volt's not very high, all you have to do is just swap out this voltage source for 2 volts or to 3 volts, and you can go between any value between 0 and 3 volts. So, yeah, so I'm now going to talk about accuracy and things of these, like that. But in 25 minutes, we've covered all the digital to analog conversion you'll ever really need to know. So this is it. There is no better circuit than this. This is the excellent circuit. And if you look on sort of open up devices, you'll see resistor networks in this shape actually on the board where they're actually being used. So it's a very, very ubiquitous circuit. Any questions on this before I carry on? Just stick up your hand. Very happy. If anything's not clear, very happy to go over it again. Everybody happy? Vaguely happy? Okay. Who's happy? One person's happy. Anybody not happy? Okay, indifferent. It's quite warm in here, isn't it? Okay, so now I'm going to talk about accuracy. Now, as you can imagine, I think we looked at shaft encoders. So we looked at disks with binary patterns put on them to do sort of encoding of the robot's position. And remember, we did some sums on there, and the result was effectively that the more bits you use on your shaft encoder, the more accurately you can judge the position of where the robot is. Well, it's just the same here. The more pins you put on your R2r ladder, the more accurate you can have your voltage. So if you've got 3 pins, so you can count up to with binary. So there's 1, 2, 4. So 4 plus 2 plus 1 is 7, plus 0 is 8. So you can count up to 8 here. So you've got eight like numbers of precision, which means if you're trying to generate a voltage between 0 and 1 volts, you can sort of select your voltage in steps of 1 divided by 8. So I don't know what that value is. But the point is, the more bits you have on your digital to analog converter, the smaller these steps get. So So if you have one with a huge R2r ladder, then your step size, your voltage step size gets much smaller, and you have a much more accurate converter. So when you go and buy a digital to analog converter, it'll say on the box like 8-bit, which is rubbish, or it might say 32-bit, which is okay. Or on the really good ones, it might say 64-bit precision, which means it'll have 2 to the power of 64 levels it can detect the voltage on. But it will not be able to detect the voltage any more accurately than that. So that's an interesting, useful fact for when you're choosing digital to analog devices. Right, so what we can do now is, so do you remember in the lab you used machines that looked a bit like this to generate sine waves? In fact, you didn't generate triangle waves, but you basically used a sine wave generator in the analog electronics lab. And it looked a bit like that, and you could dial in the frequency of the sine wave and whatnot. What it had in it was an R2r ladder, just like this. And all it was doing to synthesize that sine wave is it was switching on and off these switches very, very fast to produce a wave that looks like this. Now, I've done it in sort of a stepped fashion here, but it had a much better resolution, so it could sort of fool you into thinking that the wave you're getting out was actually a sine wave. But in fact, it was a digital wave that it was synthesizing using an R2r ladder. And what you sometimes do, just to smooth out the output a bit, is just pop a capacitor here, just to make it get out any rough edges. But in principle, you can now build instruments that can go from the digital world to the analog world, just like this digital to analog converter used in the lab to generate sine waves. And what we can now do is we can literally attach a speaker to this network, like literally, and we'll get music out of it. It's that simple. So you now generate music. There's nothing clever about this at all anymore. You've sort of conquered digital to analog converters. What time is it? Shall I wake you up with something? You're all getting a bit sleepy. I know. What I'll do is I'll go right to the end of the lecture. I've got something prepared for you. That's hammered digital analog converters to death. Okay? So you can now build Tesla cores that make music, which seems like a good thing. Okay. So now we need to go the other way. We need to go from analog to digital. And actually, you've done most of the work for this already. So although we've made a converter to go one way, we can actually sort of reuse it to go the other way. And it's quite quick and easy. So before we can do that, we need to learn about something that's called a comparator. Now, does anybody recognize that symbol? What's that symbol? What was it before? Huh? Op-amp, I heard down there. Yeah, it's basically an op-amp. Now, a comparator is basically an op-amp that's specifically designed, well, it's designed in a very slightly different way. It's basically the same device, but we're using it very slightly differently, and it's been optimized to do a very slightly different task. So in this setting, this triangle is called a comparator. And the point of a comparator is it compares two values. So it compares one voltage and another voltage. And it's very simple. Now then, it basically compares this pin to this pin, and the output it'll give you is either a 1 or a 0 based on what it thinks the difference is. So if this pin is if 2 volts is smaller than 4 volts, it gives you 0. Then if you raise the voltage of this pin to say 5 volts, it gives you a 1. So it literally just compares the two numbers, and if this one's bigger than this one, it goes from a 0 to 1. Or if this one is smaller than this one, it gives you a 0. That's comparator. Nothing to it at all. Okay, it compares two numbers, gives you an output depending on the voltage. So what we can do is we can stick a comparator on the output of our R2r ladder. Now imagine we want to measure this voltage here. Imagine we want to measure this voltage. Imagine this is a voltage we're trying to measure with a battery or something like that with a voltmeter. What we do is we do the following. We firstly apply 1 to this pin, and we get this voltage here, okay? Output of the comparator is 0, because it's smaller than this voltage. Now we apply 1 here. The voltage here goes up a little bit more. Output of the comparator is still 0, because this voltage is still smaller than this voltage. We increase again. This voltage goes up a bit more, and the output is not changed to the comparator, because this voltage is still smaller than this voltage. Increase again. Can you see this voltage all the time is getting closer and closer to this voltage we're trying to measure? Increase the voltage again. Output's not changed to the comparator. Now this is the magic step. Increase the output from our digital to analog converter 1 more. And suddenly, this voltage V out has gone over the voltage we're trying to measure. So now all of a sudden, this voltage is bigger than this voltage, and the output goes from a 0 to a 1, and it's flipped. So this bit's flipped. Suddenly, the output of our comparator has gone from a 0 to a 1. Now what we can do is we can get, basically, a computer to drive this, to put a series of, so to count up, to go 1, 2, 3, 4, 5 on this digital to analog converter. And whilst it's doing this, it can be monitoring this bit, just waiting for it to change. It increases it, it goes, is it 0, or is it 1, is it 1, is it 1, is it 1? So it's continually increasing the voltage on the output here, continually monitoring this output here, and just waiting for that bit to flip. And as soon as that bit flips there, then the computer knows that whatever voltage it's producing at this pin is basically around about the voltage it's trying to measure. Yes. Now then, any questions on that? I'm going to show you one in action first, actually. So here, if I can switch to here, I've got the sort of the quintessential analog to digital converter. So this is a voltmeter, and you've used these in the labs. Now I've got this set on the ohms reading, so it's measuring measuring a value. So if I cross these pins, so we get 0 ohms. Okay, can you see it says 0, 0 ohms? Yeah. Now this is the thing. When I disconnect these wires like this, so it will now measure infinite ohms. So going from 0 to infinite ohms. Can you see this value here? It's counting up, counting up, counting up, counting up, and it's not quite sure. So we'll do it again. It doesn't instantly tell you what the resistance is. It has to like count up. But what it's doing, the reason it's not an instantaneous display is the computer in the voltmeter is basically counting up with an R2r ladder and waiting for this bit on the end to flip. That's how it works. So it's quite a slow process, and it can take a couple of seconds to go through all the bits, especially if you've got like maybe 32 or 64 bits. So that's the reason these things are quite slow. Any questions about this? Maybe not sure about how this works? Shout out. Okay, so now what we're going to do, the final thing, we're going to do flash converters. Now, at the back of this lecture, I've got a camera, and it's recording me in HD. And across this screen, there might be 700 pixels, and above there's 400. And each one of those pixels is going to need an analog to digital converter. And you can't have a video image like waiting and counting up, doing this counting up in the R2r ladder, because by the time it's gone through its conversion process, I'll have moved and the picture will be all blurry. So we need something quicker than a comparator and an R2r ladder when we're trying to do very, very fast video conversion and audio conversion, things like that. So what we need is something called a flash converter. And they're flash converters because they're very quick. So I'm going to talk to you about flash converters. So then, these are slow. So there we go, I've just said this. Now, again, a bit of interactive. So we've got 4 resistors, all called R. 1, 2, 3, 4. What will the voltage with the arrow be? Come on, somebody shout. Go on, I've showed you videos and everything. You've got to shout out now. What about the man yawning? There we go, got you. What's the voltage going to be there? 4 resistors, 1 volt over it. 1 volt at the top. You're dividing it by 4. 0.25, fantastic. What's that one going to be there? 0.5, almost. That one there? Yes, and the final one's obviously really easy, yeah? So we got basically a potential divider. Now what we do is we put a wire in with with what we're trying to measure. So here's the voltage coming off our pixel in our camera or our microphone or whatever. Now what we do is we put in a whole series of comparators, okay? So here I've got 3 comparators. And what I then do, so at the moment we've got 0 volts on the input. And you can see, if you look at it, that 0.25 is, so 0.25 is smaller than the input, so we get a 0. 0.5 is smaller than the input, so we get a 0. 0.75 is smaller than the input, so we get a 0. Now, what happens when we increase the voltage on the input to say 0.265? So you can see the input voltage is now just 0.01 volts above the voltage going into the first comparator. And you see the first comparator's gone to a 1, and we get 2 zeros. Now this process is basically instantaneous. Then when we increase the voltage again, you see that this voltage coming in is now 0.051, and that's bigger than this voltage and this voltage. So this comparator goes on, this comparator goes on, and this comparator's still off. And finally, if we put in 0.9 volts, that's bigger than all these values, and they're all on. So you can see this gives us instantaneous conversion between analog and digital. And this is called a flash converter. You can buy these in chips, and they're very handy if you want to do something conversion very, very quick without having to count up. Yeah, and then all you do is this, all you do is you stick, so these inputs that come out of here aren't actually binary. It's like, it's not quite binary code. So you need a block to convert this code here to actual binary code, just a block of digital logic. And that's it. Yeah, and I've given you the little video already. So any questions, you can ask me now, or I will be in the examples class tomorrow morning at 9 o'clock with Arthur. And we'll be running over some example sheets tomorrow. And I'll put this online in a minute when I get back to my office. Okay? Thank you very much for your attention.